Bohr model the atom. So we've already gotten a decent amount of exposure to this in our simulation and in our discussion yesterday with our lab, but today we're just going to look at it a little bit more in depth, kind of talk about the nitty-gritty details of that model of the atom. So just like with Rutherford's model of the atom, we have our positive nucleus at our center. Okay? So we have that positive nucleus with our protons and neutrons at the center of our atom. What the Bohr model does, though, is it explains what our electrons are doing. So according to the Bohr model, we have these different orbits or energy levels on which our electrons. Okay. So around the nucleus, we have energy level or orbits that contain our electrons. Our electrons are going to start out in the ground state, or that energy level closest to the nucleus. That energy level closest to the nucleus, or our ground state, this is going to be a very low energy state for our electron. So this is where our atom is most stable. Okay? That's because our negative electrons and our positive nucleus are attracted to one another. So this is where our electron is very happy. It's going to be really hard to remove or to move our electron from that ground state. However, if we do want to increase the energy of that electron, move it to a higher energy level, we would need our electron then to absorb energy. If our electron absorbs energy, then we can move to a higher energy level. Okay? And the farther we get away from that nucleus, the less stable our electron is, the more energy it's going to have. The further from the nucleus, the more energy our electron has. Okay? And this is going to be what we call an excited state. So when we move to a higher energy level, that's going to be what we call an excited state. Because when you're excited, you have more energy. Okay? So since our electron is happiest when it's closest to the nucleus, that's where it's most stable, it's not going to be able to stay at the higher energy level for very long. Okay? And when it comes back down to the ground state, or back down to the level closest to that nucleus, our electron is going to release energy. So in moving from a higher energy level back to our ground state, our atom is going to release energy. And it's going to release energy in the form of colored light. So the different colors that we saw in our lab yesterday corresponded to the different energy levels that our electron was popping in between. Okay? So we can kind of predict the bigger the drop in energy, or the bigger the drop in energy levels, the higher or the more energy we will release. So each color that we see in the emission spectra corresponds to a specific change in energy levels. Since our electrons cannot live in between those orbits, we do not see a continuous spectrum of light. Okay, those wavelengths are very particular into what this change of energy is. Okay, and that change of energy, that specific change in energy that we have between our levels, we are going to call that a quanta of energy. Okay, so when we talk about a quanta of energy, think of it as a quantity. Okay? That is going to be a very specific quantity of energy that is either released or absorbed as our electron moves between energy levels. Okay? Since our electrons cannot exist in between levels, we can only absorb or release specific amounts of energy. So we're only going to emit or absorb lights of specific frequency and wavelength. That's why when we looked at our emission spectra in the lab, we saw those very distinct lines rather than a rainbow. So since we can only observe specific wavelengths of light, our emission spectrum is not continuous. Okay? We can't see a nice array of colors. We can only absorb the colors that correspond with those different quantities and energy. Mm-hmm. Of the atom, we have our positive nucleus at the center. Surrounding that positive nucleus, we have different energy levels or orbits that our electrons can exist. Our electrons start out in the ground state, that is the lowest energy level, closest to the nucleus. Okay, that's because our negative electron and positive nucleus are attracted to one another. If we want to move that electron farther away to a higher energy level, it needs to absorb energy. And when it moves to a higher energy level, that's what we're going to call the excited state. Okay, because when we're excited, we have more energy. What energy level we move to depends on what quanta or what quantity of energy that we absorb. Okay, because electrons cannot exist in between those orbits or in between those energy levels. Our atom can only absorb specific amounts of energy that allows that electron to make the full transition to the next energy level. When the electron then returns to the ground state, so it moves from a higher to a lower energy level, it's going to release energy in the form of colored light. Okay, and that is why when we did our flame tests and our atomic spectra, we saw those different colors of light for our substances. And again, for that emission spectrum, the reason why we didn't see just a continuous blur of colors is because we can only release specific wavelengths of energy. Okay, so those specific wavelengths that correspond to the distances in between our energy levels. Okay, what we're going to look at next is how we can calculate how much energy we're releasing or absorbing. Already remember that as the energy of our wave increases, our frequency or how many crests we have per second also increases while our wavelength decreases. Now, on the opposite side, as energy decreases, our frequency is also going to decrease and our wavelength is going to increase. So as energy decreases, our crests are going to get further apart. So we have less crests per second. We are actually going to have an equation that allows us to calculate how much energy an electron has or a photon has. And that's going to be that our energy is equal to a constant h times our frequency. H is going to be something we call Planck's constant because he came up with this equation. So of course we have to give him a little shout out. And that H, or Planck's constant, is always going to have a value of 6.626 times 10 to the negative 34 joules second. Okay, so whenever we use this equation, we're always going to use that value for H. And then remember, this little nu tells us our frequency. Okay, so let's look at an example of a wave whose frequency is 3.38 hertz. Remember, frequency we always want to have in hertz. So if we look at our equation, E is equal to H times our frequency. So our energy is equal to 6.626 times 10 to the negative 34 times our frequency, which in this case is 3.38 hertz. So to find out how much energy we have, we'll plug this in our calculator. And we should find that this wave has 2.24 times 10 to the negative 33rd joules of energy. Just like how frequency always has to be in hertz, wavelength always has to be in meters, energy is always going to be measured in joules. Okay? So in this example, we were given our frequency, so we're able to just plug that into our equation. What if, however, we had an example where we didn't know our frequency, but we knew our wavelength? Is 9,330 centimeters. So if we look at our equation, energy is equal to H times frequency. We are not given frequency here. We're given wavelength. So we need to think, what other equation do we know with wavelength? And that is going to be that our speed of light is equal to wavelength times frequency. Okay. We can see that we can use this equation to solve for what our frequency would be of this wave. Because if I divide each side by my wavelength, I'm left with C, or the speed of light, divided by my wavelength is equal to my frequency. Since 3 times 10 to the 8th, or C, divided by wavelength is the same thing as my frequency, I can actually plug this right in to my equation for energy. This is going to create a new way to write our energy equation. And this is going to be that our energy is equal to H, and instead of times frequency, we times C divided by wavelength, where H is still that 6.626 times 10 to the negative 34th, and C is our 3 times 10 to the 8th from our speed of light. Okay. Now I have an equation with wavelength that I'm able to use for this example. The one issue is, though, that I need my wavelength to be in meters, and this is given to me in centimeters. So that is going to be our first step. Find out how many meters are 9,330 centimeters. So we'll need to remember that there are 100 centimeters in 1 meter. Okay, that means in this wave we have 93.3 meters. We are now able to plug this wavelength, now that's in meters, into our equation. So we'll do E is equal to H, or 6.626 times 10 to the negative 34th, times C, these are 3 times 10 to the 8th, our same constant from our previous wave equation, all divided by our new wavelength in meters of 93.3. Okay. And when I plug that in my calculator, I am going to see that my energy here is 0.13 times 10 to the negative 27. And that is, of course, in joules, because energy is always going to be in joules. Okay. So even if we don't know our frequency, we can use this equation that our energy is equal to H, our 6.626 times 10 to the negative 34, times C divided by our wavelength. Where C, remember, is our 3 times 10 to the 8th, and that lambda represents our wavelength in meters. So depending on what you're given in your problem will determine which one of these equations you want to use to figure out how much energy your atom released or absorbed. Backwards. Here we want to find the wavelength of a wave given its energy in kilojoules. So here, remember, we have two energy equations. E is equal to h times frequency, or E is equal to hc over our wavelength. Since we are looking for a wavelength, we'll want to use our equation that includes wavelength. So that second one. Something to keep in mind here before we start plugging in values is that energy always has to be given to us in joules. So we are not able to just plug in this 1.78 times 10 to the negative 12 kilojoules of energy into this equation just yet. Our first step is going to be to convert it in to normal joules. So we remember that for every 1 kilo thing or 1 kilojoule, we're going to have 1,000 things for 1,000. So we plug this in our calculator. We have 1.78 e to the negative 12 times 1,000. We'll find that this wave will have 1.78 times 10 to the negative 9th joules of energy. Okay? Now that we've converted it into joules, now we can solve it for our equation. So we can do 1.78 times 10 to the negative 9th is equal to hc over our wavelength. Before I plug in the values for my h and c, just to make it a little bit easier on ourselves, I'm going to get wavelength by itself first. Okay. So in order to get wavelength by itself, I need to get it out of my denominator. So I'm going to multiply each side by wavelength. This leaves me with wavelength times 1.78 times 10 to the negative 9 is equal to hc. Now I can see that if I want to get my wavelength by itself, I'm going to have to divide each side by my energy. Okay. Now that I have wavelength by itself, now I'm at a point where it's an easy position to plug in the values that we know. So we know h is always 6.626 times 10 to the negative 34th. C is always 3 times 10 to the 8th. And we're going to divide that by our energy. So 1.78 times 10 to the negative 9. And again, this is where it's always super helpful to use that E button, because then we don't have to worry about parentheses in my denominator. So when we divide, what we're going to plug in is we'll do divided by 1.78 second E negative 9. And we should find the wavelength for this wave then is 1.12 times 10 to the negative 16 meters. Because remember, wavelength is always given to us in meters. All right, so I hope that helps. To find our energy of a wave, we're always going to use either one of these two equations. It's just a matter of, do we know our frequency or do we know our wavelength? And that'll help tell us what equation we need to use to solve for our energy. Okay, always just make sure that you have the correct units for those variables. Please let us know if you have any questions. Otherwise, I hope you have a great day.